Here now a direct translation leads to this first statement right here. Notice that we're given in a natural number. A natural number is just a positive integer such that 2n+1 is a perfect square. Now we're supposed to show that n+1 is the sum of two consecutive perfect squares. All right, and so this information is given. This information is implied. K has to also be an odd number, since if it was an even number, when you square an even number, you get an even number back, right? So this is definitely an implication of the givens. Now, so we write 2n+1 as k squared as a given condition. Now, and then we use this result right here. Now, you guys will recognize right here that this is just 2n+1 quantity squared. I'll just put it parenthetically above. 2m plus 1 quantity squared. Okay, is that piece right there? Okay. Now, notice if you subtract 1 from both sides and divide by 2, you get n is equal to this. Okay, n is equal to 2m squared plus 2m. Okay, so if we add 1 to this expression, we just bump the 1 on to the end of this expression, right? Now, I got stuck here initially, but it's really obvious if you just look at it. This really stumped me. I couldn't believe it. I was thinking, well, this doesn't look like the sum of two squares. But all you have to do is split this one apart, meaning we can write this as m squared. Okay, just split the 2m squareds into a pair of them. All right, I mean, it's so simple, but I didn't notice it initially. So we have m squared plus m squared again, plus 2m plus 1. Okay. And it's amazing how often I get stumped by simple observations like this. Just didn't notice it initially. So 2m plus 1. Then at this stage, you just have to recognize that this piece right here is a binomial squared, right? That guy right there. So what we get is that this is equal to m squared plus the quantity, which is the next consecutive square, here we go, folks. And so that completes the proof. Now, I do want to work at least one concrete example, or exactly one concrete example. But notice this is what was called for, two consecutive perfect squares, and we've written it just that way. So we can go ahead and write, thus we have demonstrated, QED, quandam est demonstrandum in Latin. All right. Now, again, let's just take a look at maybe at one special case right here. Notice that I did this one before I did the video, so I don't have to do too much thinking here. But notice that we can write, if we use this as our key statement right here, we can write 2 times 84 plus 1 is equal to 169, right? But that's a fairly well-known perfect square, right? 169 is the same as 13 times 13, and we can write that as 13 squared. Now, what made this one kind of a hard problem is you have to make sure, I'm not saying hard, but you just have to keep everything straight. That would be the n right here, right? And so you would have 84 plus 1 using this piece right here, which is what the problem called for. 84 plus 1 equals 85, right? But this is not too hard to see directly without having to use the formulas here. Let me get some more space here. So you have 85, okay? But notice that is equal to consecutive squares, right? That's 6 squared plus 7 squared. Pretty cool, if you ask me. This, of course, is 36, or I'll just write it over here. That's equal to 36 plus 49. So that's guaranteed. Anytime you have an n that enjoys that property, it's going to be able to, you're going to get this condition. Okay, 36 and 49 is equal to 85 last time I checked. But anyway, I hope you enjoyed that one. I liked it a lot.